Welcome to the session. In this session, we will discuss about the mathematical modeling of DC motor. As we already discussed, in the DC motor, when we supply the voltage, it will result in speed, and supply voltage will result in current depending upon the parameters of electric winding, resistance and inductance. Current will produce the torque according to the magnetic circuit, and the torque will produce the speed of the shaft or rotor according to the parameters of the mechanical parameter of the rotary part, that is friction and inertia. So let's represent the complete system of DC shunt motor in the form of mathematical equation, so that equation can be used later to develop the simulation model of the DC motor. So we will try to represent to find the transfer function of each transition, that is voltage to current. Voltage produces the current, so current is output and voltage is input. Current produces the torque, torque is output, current is input, and torque produces the speed. Speed is output and torque is input. We will also see the feedback loop that exists due to the magnetic circuit in the session. So we will use the DC shunt motor, the simple circuit diagram of DC shunt motor. When we supply the voltage, the current will flow through the armature winding, and it is shunt motor, so shunt field winding is connected parallel to the armature, so same voltage is supplied and ISH current will flow through the shunt winding. So if we represent the DC motor as in the form of winding and back EMF, this back EMF is the voltage produced across the conductor according to the Faraday's law. So when conductors are rotating in the magnetic field, the EMF will induce in the opposite direction according to Lenz's law. So satisfying Faraday's law and Lenz's law, EMF will induce across the winding, and it's called the back EMF EB. So total voltage appear across the winding will be the difference of these two. We will simply represent the write the mathematical equation with the help of Kirchhoff voltage law. So during the steady state condition, we know only the resistance is matter, and if we want to know the performance during starting also, when speed is not constant, inductance also comes in picture. So winding has its resistance and inductance, armature resistance and armature inductance. It's the resistance of shunt field winding, constant current is flowing, but we are currently not interested in starting current of the shunt field winding. It will remain constant after the switching. So let's write the Kirchhoff voltage law equation, KVL. From the KVL we can say supply voltage is equal to IA into RA, voltage drop across resistance, then voltage drop LA into DIA by DT, and plus this back EMF. So if we rewrite the equation in this form, so V minus EB, so this is the voltage difference that will appear across the winding, and if we apply the Laplace transformation, then we can write I is common RA plus S into LA. So now, as I already told, we require the transfer function, output by input. So voltage produces current, so IA is the output. This voltage difference is the appear across the winding and is equal to 1 by RA plus S into LA. So this is the mathematical equation of our first transition from voltage to current. It can be represented in the block diagram in this form. So input is voltage, that is V minus EB, and output is current IA, and transfer function, that is constant 1 by LA into S plus RA, or say RA plus S into LA. Simply if we write the same way for the shunt winding, supply voltage is equal to I into R, ISH into RSH, plus if we also consider the inductance of shunt winding, LSH into dISH by dt. But if we only interested in steady state value of current, because once we switch it after fraction of second, the current will remain constant and it will always V by RSH, because as long as we are not going to change this voltage, we are not interested in the field control, then this current will remain constant, V by RSH. Let's say now transition from current to torque, how current produces the torque and how we can represent it. So simply for now we will use the linear relation and use the constant. Torque is proportional to current and we use the constant Kt to represent that. So output is torque. So torque developed by armature current Ia is equal to constant Kt. So that can be represented in the block diagram like this. Input is current, output is torque and constant is Kt. Linear relation. Now if we look at the how torque develops the speed, and if we try to write the equation of that, then we can say that torque is equal to J d omega by dt plus b omega plus load torque. So these all are torque opposing to the supply torque. Omega is the angular velocity. So J is the inertia of rotor of the motor when load is not attached, so we can say the no load, so inertia of only rotor. B is the friction of the say bearing and air when rotor is rotating inside the stator or inside the motor. So these constant are only represent the parameters of motor or say rotor, and plus this is the load torque, so it may be have several different characteristics according to load and it is opposing. So if we rewrite the equation in this form, the torque developed minus load torque is equal to J d omega t by dt plus b omega. If we apply the Laplace transform, then we are having this form, Te minus TL is equal to omega into Js plus b. So we can rewrite in the transfer function form, output by input. Output is omega speed, input is torque. This is also difference in torque. Torque developed minus load torque, that is opposing, is equal to 1 by Js plus b. So we can represent the same in the block diagram form in this form. So input torque Te minus TL, output speed omega radian per second, and transfer function 1 by J into S plus b. Now let's say this is the feedback loop when speed produces the voltage. So voltage is back EMF. So now we are talking about the back EMF. Back EMF will depend upon the speed. Higher the speed, higher will be the back EMF. Because shunt field winding current we are assuming the constant. Otherwise back EMF also depend upon the flux that produced by the main pole, and that is by the shunt field current. So back EMF is only proportional to the speed and constant is Kb. So output is back EMF, input is speed. So speed produces the back EMF and constant is Kb. So we can represent the same thing in the form with the arrow. Speed produce the back EMF with the constant Kb. Speed to voltage. Now if we combine all these things, all this transfer function, then we will have the complete model of the DC motor. So here it is. Now you can see this is the what we first discussed. Voltage produces the current. Voltage is difference of V minus Eb. Then current produces the torque and gain is Kt. So Te by Ia is constant Kt. Then if you look at here, Te minus TL produce the difference in torque, produce the speed. Here we have used the summation summing point to represent. So we can supply the value of load torque over here. If it is 0, then it is only torque developed. So this way, and we can also use the speed develop the back EMF. So we are taking feedback from here, and the speed omega will responsible for the production of back EMF, which is governed by the constant Kb. And here we come back our EB, and this is the supply voltage minus EB. So this point will become again V minus EB. So this is complete block diagram of the DC motor. It's represent the mathematical equation. This is differential equation, this is linear equation, this is again differential equation, and this is linear equation, and this is summing point and summing point. So this way differential equation and linear equation represent the DC motor. So this is called the mathematical modeling of DC motor, and this equation, differential equation, represent the mathematical equation of DC motor. So we can develop this motor now in the Simulink model of the MatLab, as we know, and we will examine the different thing in the MatLab Simulink model of DC motor. So after that, if we supply the specific amount of voltage, if the parameters are known, Ra, La, Kt, Kb, J, and B, then we can have idea about the what will be the steady state speed, how speed will rise, and this all things, and dynamic response of speed can be known with the Simulink model. So this is the mathematical model of DC motor.